Hello and welcome everyone. My name is Mansi. I'm a faculty member at the California Institute of Technology, and I'm also the principal investigator of the Growth Project. So on behalf of the entire Growth team, I extend all of you a very warm welcome to our annual Growth School. For the first time, we're doing it in this virtual format. And I'm happy to report there was a lot of excitement and enthusiasm. There were over 800 applications from 80 countries. So I really do hope that all of you enjoy the coming week and learn things about our universe that will be fun for you. So the goal for today is to give you an overview of time domain astronomy, motivate you for all the wonderful tools and techniques and data analysis methodology you learn over the week, and give it some context, some broader context of some excitement in time domain science. The goal of the second session today, right after this one, will be Python basics, just getting you to speak fluent Python so that you can really then blaze ahead on the other modules. So let's get started. The first concept I want to explain to you is the concept behind growth, right? So growth is an acronym. It stands for Global Relay of Observatories Watching Transients Happen. And the concept behind this is how do you beat sunrise? Okay, so let me explain that. So let's say you have a really fast moving asteroid, or you have a really fast fading transient, or a young supernova that is fast rising, anything that's changing quickly in time, right? Anything that's dynamic in our universe. So if you're looking at that, let's say from your favorite mountaintop with your favorite telescope, you can collect some data. But if you want to see how that changes as a function of time, at some point the Earth will just rotate and the transient will set for you, or the sun will rise and you will not be able to observe anymore. So the concept behind growth is to make friends with people around the globe and pass the baton westward, right? So if you're observing in California, you move west to Hawaii, then Japan, then Taiwan, then India, then Israel, so on and so forth. So by making this ring of telescopes that are longitudinally distributed, you can continue to beat sunrise and get an exquisite data set when monitoring fast moving transients or fast evolving transients, rising or fading. So growth is a partnership in international research and education. This is a special program under the National Science Foundation. And we have 16 partner institutions in 8 different countries that you see listed here. And one of the growth telescopes is the Liverpool Telescope. And our hosts for this virtual school are actually Professor Chris Copperbeat and Professor Dan Purley at the Liverpool Johns Moore University. And you'll have a special treat because on Wednesday you have an optional session, but it may quite well be the most fun session of the school, where you'll get to move this beautiful robotic 2-meter telescope and collect data from it in real time. So I strongly recommend you attend Professor Copperwheat's special observing session on Wednesday. And you'll note that if you looked carefully at the globe, the location of UK was not where the United Kingdom actually is, but it was down in La Palma, Spain, where the telescope is located. There's better weather there, let's just say that. Now, growth is more than just telescopes. Growth, really the more important core behind growth is that it's a network of people. It's the most amazing, most fantastic team that I've had the privilege of working with. And it's a team that never sleeps, because guess what? It's daytime somewhere, sometime in this ring of people all the time. So we can really have a lot of fun and work 24/7 here. Here I'm showing you pictures of my co-PIs at each of the different growth partner institutions. But truth be told, the real heart of growth, the real powerhouse of growth are the young people. The graduate students, the undergraduate students, the postdoctoral fellows, they are the true powerhouse of growth. So here you see pictures of some of the growth students and postdocs. This is actually taken in August 2017 when they were somewhat sleep deprived, and you'll hear more about why later in this talk. But they're still smiling, they're having fun. That's the important thing. And what we do scientifically in the Growth Project is time domain astronomy, and especially multi-messenger astrophysics. So let me explain what this word that you may have come across actually means. Right now, there's a lot of excitement in the field of multi-messenger astrophysics, particularly because multi-messenger astrophysics allows you to study an astrophysical object from multiple different messengers. You could have gravitational waves, you could have neutrinos, you could have ultra-high energy cosmic rays, and you could have electromagnetic light across the electromagnetic spectrum. And what's cool is that each of these things that I'm listing here is an advance in sensitivity by nearly an order of magnitude. And this advance in sensitivity, anytime you advance something by an order of magnitude or more in sensitivity, the universe cooperates and shows you some cool, fun secrets that it has to offer in that regime that you hadn't explored before. So let me give you a few concrete examples that I've chosen from the middle of the electromagnetic spectrum. So the highest energy is the gamma rays, the lowest energy and the longest wavelength is the radio. And I'm going to give you examples from the middle of the spectrum from the UV, optical, and infrared. So let's begin with the optical. There's been a revolution of sorts to build larger format, wider field cameras in the optical regime. And you can see that the full moon, which is half a degree on the sky, is that little tiny thing on the screen. And the detectors are way bigger. The biggest camera that we have right now in the optical is the Zwicky transient facility, which is a whopping 47 square degree camera. And what that allows us to do is imagine just stepping outside and looking at the Orion constellation. In one shot, you can get the full belt, the sword, the Horsehead Nebula in just 30 seconds. So if you can image such a big piece of sky so quickly, that means you can survey something like 3,750 square degrees every hour. And you run out of sky to observe in just a few hours. So what you end up doing is not just making beautiful static images of the sky. What the capability that you have with these wide mosaics is to build movies of the sky. So it's quite literally imaging the same sky over and over again and looking for bright flashes that may change. So this is what we call quite literally celestial cinematography. Yeah. So this was in the optical regime. This Zwicky transient facility at Palomar Observatory is breaking new ground there. Let me give you another example of a telescope just next door to it. This is the Palomar Gattini-IR telescope. And the powerhouse behind this is graduate student Kishale Day, and you're going to hear more from him later in the school. And what is amazing about Gattini is that it's opening up the dynamic infrared sky for exploration. So the camera that's behind this modest 30 centimeter telescope is a 25 square degree camera. And 25 square degrees in the infrared is a factor of 40 larger than any other infrared camera out there. The second largest camera right now is 0.6 square degrees. So this wide field, albeit with coarse spatial resolution, opens up an entirely new window to the universe. And I urge you to talk to Kishale more about this project. The sensitivity in the infrared to the next step, also on Palomar Mountain, also not very far from either ZTF or Gattini, is a brand new telescope that we are putting together called Winter. So this will be on a much bigger telescope. Instead of 30 centimeters, we're targeting a 1 meter telescope. And we're using a new type of semiconductor technology to get finer pixel scale. So we'll get 1 arcsecond per pixel on these in-gas detectors. So that's another thing that will come online, hopefully next year. Now, I told you about the optical, the infrared. So I wanted to also tell you about the UV. The UV, we don't have any wide field images whatsoever. And UV can only be studied in space. So you need to launch a telescope on a satellite before you can do anything wide field ultraviolet. The good news is that just a few months ago, NASA approved a wide field ultraviolet mission on CubeSats. This mission is called Dorado. And you'll hear later in the school on Friday by Dr. Brad Senko from NASA Goddard Space Flight Center. And he's the principal investigator of this mission. So please do ask him more about wide field ultraviolet and what that could do for you. So here's a picture that I want you to keep at the back of your mind, a beautiful mountaintop in Southern California, Palomar Observatory. It has the venerable Palomar 200-inch telescope that's been around for over 70 years. And then it has these brand new robotic telescopes all surrounding it, which can do robotic optical, robotic infrared, robotic spectroscopy. And that's what's making this a transient factory. That's what is driving a powerhouse in discovery space for new types of optical transients. So I'm a bit biased. This is my favorite mountaintop. So I had to show you a picture of this before I tell you more. But once you have a discovery engine like this, a coordinated network of telescopes around the world can attain what is critical follow-up data to understand the astrophysics. So if you have found a nice new flash of light, it could be anything, right? You don't know what it is unless you take the light and you disperse it through a spectrograph and you see the chemical signature, the elements involved, the redshift, the energetics, and that is what will give you the astrophysics and the astrochemistry of the transient. So how do we go about, hundreds of thousands of new flashes of light, new transients that we're discovering and coordinated amongst these 18 telescopes around the world? And the methodology that we use, this tool that we use is something that we call the Growth Follow-Up Marshal. And it's a dynamic collaborative platform that it's basically a Facebook page, to put it simply. And here we have the continuous chatter of, who's observing what with which telescope, which targets are being assigned to which marshal, the way to which telescopes, what new data is coming in, what are we learning about it, which ones are exciting, which ones are not, etc. So it's a non-stop dynamic database with input from all the different people and all the different telescopes and multiple different discovery engines, be it ZTF or Gattini or something that we just saw from Astronomer's Telegram here. So what this does is that it lays a foundation now for the publications, for the papers that we want to write, for the discoveries we want to share with the world. And in the last 5 years, I'm happy to report that the growth network of people has been immensely productive. 168 papers have been written for a variety of different journals with an H index, a citation index of 39, which is pretty cool. The best part for me about these publications is that majority of them, the first author, the lead author, has been a student or a postdoc in the growth team. So there's no way for me to do justice to all the wonderful results from the growth team. But what I want to do for you now in the remaining time is give you 3 examples of some science results to whet your appetite and to just keep you motivated for the rest of the week when you learn how to work with multi-wavelength time domain data. So the first example I want to give you is from our own Milky Way galaxy. This is a lovely discovery by graduate student Kevin Birch on a 6.9-minute eclipsing white dwarf binary. Right? So imagine the number of times this binary is going around each other while I'm giving this talk. Now this beautiful light curve that Kevin published also shows how the period is decreasing as a function of time. So gravitational waves get emitted when 2 compact objects circle each other, and then they're going to eventually merge. Now these uber compact white dwarf binary systems are fantastic sources of gravitational waves in the LISA frequency band. So when the LISA satellite gets launched, this will be a booming signal for LISA. And on Growth School Session 7, Dr. Melissa Hayes-Gerke will talk to you about light curve analysis. How do you study periodic objects? What do these eclipses mean? So you'll learn more about that on Thursday. Now let's switch gears a little bit to solar system science, really, really close to home. And here I want to highlight the work of 2 growth postdocs, Bryce Bowman and Quan Jie. This picture that you see here is of an interstellar visitor that some of you may recognize. But in addition to interstellar visitors, these 2 postdocs have worked on asteroids that are called Atira and Vatira objects because they're inside the orbit of Earth and inside the orbit of Venus. They also study near-Earth objects that are relatively small but can cause a lot of damage if they make it through the Earth's atmosphere. So they're keeping a close eye on planetary safety for us here. And you can look them up on EDS to read about their work. Now, the third example that I want to give you is actually a multi-messenger example. So I'm going to spend some time dissecting this example in detail. And the idea is that it gives you a flavor of how you use the multi-wavelength data to address two scientific questions about one object. So this one object is a neutron-star merger that occurred on August 17th, 2017. So the growth team has published many papers on this. The first 3 papers were published in the Science issue for the 2017 Breakthrough of the Year. So that's what you see, this artist sketch here. But I'll tell you more about what we learned here. So on August 17, 2017, for the very, very first time, we detected gravitational waves from a binary neutron-star merger. Now, by this point, the Nobel Prize had already been given for 2 black holes merging. And you can see black holes merging are actually not that spectacular in a few seconds. I mean, just for an astronomer. I mean, some people really love them, so no offense to them. But they only last for a few seconds. The whole chirp signal is over in a few seconds. This neutron star merger, because of the masses of the neutron star, lasts for 100 seconds. And it was the loudest and closest signal that the gravitational wave interferometers in the LIGO-Virgo system had actually observed. So you'll hear in a moment the chirp that follows from this long gravitational wave signal. And right now you're just seeing the cycle. So that was a chirp right there, right? So you see the merger and you hear that chirp right there. Now, based on this gravitational waveform, you can derive a whole bunch of parameters about the mass ratio, radiated energy, etc. And what made this event even more spectacular is how it lit up the entire electromagnetic spectrum, from radio through gamma rays. So across a wide range of many orders of magnitude in frequency, in wavelength, and temperature. And this is what I'm going to describe to you in some detail now. So 12:41:04 UTC, that was the time when we saw the gravitational wave chirp signal and the merge of the 2 neutron stars. The action began for astronomers 1.7 seconds later, where you see this blip that was detected by the Fermi satellite and also the integral satellite. And this was a burst of gamma rays. So these were gamma rays that were between, you can see 10 to 300 keV here. So these are extremely energetic photons that came from the same place and same time as this neutron star merger. What was even more exciting is that now the gravitational waves and gamma rays are very coarse spatial localizers. In the optical and the infrared, you can pinpoint the signal. So then began a hunt for which galaxy is the actual host galaxy. Where exactly in the sky did this event come from? And what was amazing was that there was hardly 40 galaxies in the localization. This was so high signal to noise. It was so well localized that very quickly, within about 10 hours after merger, we were able to pinpoint that this galaxy, NGC 4993, is the true home of the merger. And in this galaxy, you see that little red dot on panel D here. That red dot is what all this excitement is about. That is the kilonova, or the optical infrared counterpart to this gravitational wave merger. And why it's red and what that redness means is what I want to explain to you next. So in general, this method of mapping large areas and identifying and pinpointing the kilonova is reaching the next level. In the past year, LIGO-Virgo had their 3rd gravitational wave observing run. There wasn't an event as well localized as the binary neutron star merger from 2017. Most of the events from the past year with the 3rd gravitational wave observing run looked more like these 2 examples I show you here, where the localization is thousands of square degrees. The median was actually 4,400 square degrees. And we are searching through this large stack of hundreds of thousands of potential candidate counterparts, and we're trying to identify which one could be the true kilonova. And so here's a specific example. This was on April 26th of 2019. We got an alert, all the growth team members' cell phones rang, that there's the first neutron star black hole merger candidate. Now, when I saw this, I actually just froze for a few seconds because, truth be told, before this day, neutron star black hole mergers were a completely theoretical concept. We had never seen it before. And now there was a candidate neutron star black hole merger. We had seen two black holes merge, we had seen two neutron stars merge, but we hadn't seen a neutron star merge with a black hole. Now, this event happened to be, the phone call came at around 8 in the morning in California. So it was too late to observe from California, but thanks to growth, it was night somewhere else. And this time it was night in India. So the lovely Growth India telescope could start observing immediately, and it focused on the celestial pole. And then the sunset in Chile, and then with the dark energy camera, we were able to get the southern piece, then the sunset in California, and with the Gattini and ZTF cameras, we were able to map the rest of the area and the optical and the infrared. So within a few hours, 14.4 hours to be exact, right, we had the localization covered. And we had begun the hunt for an electromagnetic counterpart. And then once you have this candidate list, right, that's when the entire network of all the telescopes in the Growth network and around the world, even beyond Growth, to many, many collaborations begin. So what you see here is circling back to the event in August 2017. You see just the Earth rotating, the sun setting in different parts of the Earth. And you see these telescopes lighting up when they collect data on GW170817. And for GW170817, there were 70 ground-based telescopes and 7 space-based telescopes that collected data. There were over 3,000 astronomers who were actively studying it. So the data set is absolutely exquisite. Now, those of you with a sharp eye will see, there's red dots and green dots. And while the red dots only light up when it's nighttime, the green dots light up all the time. So if you haven't already figured this one out, the green dots are radio telescopes. So they're not bothered by the sun at all. Now, all of these concepts will become more clear to you when during Growth School Session 5 on Wednesday, where Professor Robert Quimby will go through observing run preparation for you. So you'll be able to understand what targets you can observe, say with the Liverpool Telescope later that night, or with any telescope. When is the best time to observe? How do you plan the observations? How do you actually go about the process of collecting the data? So now you have this exquisite data set in hand. You have all the tools from the Growth Summer School to reduce the data and analyze the data. Question is, what do we learn, right? So I'm going to give you 2 questions of what we learned from GW170817. The first question is nucleosynthesis. So specifically the question is, are neutron star mergers indeed the long sought sites of heavy element reduction? So back in 1974, theoretically, this prediction was made many decades ago. But observationally, before August 17, 2017, if you looked at the periodic table, even though the periodic table was invented 150 years ago by Mendeleev, we didn't understand most of it. We knew that hydrogen and helium come from Big Bang nucleosynthesis. We knew that all these elements in light blue and dark blue come from 2 different flavors of supernovae. But all the elements in yellow were supposed to come from merging neutron stars, but we didn't have any concrete proof. And I hope you'll agree with me that seeing is believing. And that's what changed on August 17th, 2017. So here's the data collected by the Growth team for GW170817. And the data here is shown as a light curve. So it's brightness as a function of time. And the bluer colors are the UV, the magenta shades are optical, and then the yellow-orange shades are the infrared. You can see the UV flash was very short-lived, the optical a little bit longer, a few days, and the infrared was what was the most long-lived, and that's shown in yellow and orange here. Now, it's very important that you're able to make this plot for any type of transient that you're studying. So on Tuesday in particular, please pay attention to 2 sessions, one on image reduction and the other on photometry by Professor Dan Purley, Professor Chris Copperwheat, and graduate student Kishale Day, where they'll teach you how to take an image, how to reduce that image, remove flat fields, subtract bias, etc., and then go place an aperture on your transient and extract reliable photometry. Okay, so you'll be able to make these plots after your Growth School sessions 3 and 4. Now, once you have the data across as if changing as a function of time, you can integrate across wavelength space, and you can compute what's called the bolometric luminosity. So at any given time, you're integrating the light from the UV optical infrared, and you're computing the effective bolometric luminosity as a function of time. So that's the first panel. You can also get the temperature as a function of time, the radius as a function of time, the velocity as a function of time, and now start to fit models. And when you do that, you realize that this transient is just exceptionally red. Nothing has reddened like this transient before. And this reddening is a very important clue to heavy element production. So let me explain why. So when you have elements that are getting heavier and heavier than iron, if you look at the periodic table again, you're now starting to fill not just the S shell, the P shell, and the D shell, but also the F shell. So you're talking about electrons now having millions of possible line transitions. So millions of line transitions means that the electron has many, many choices of where to go before it can escape out. So you have this very, very high bound opacity that you need to work through. So the emergent spectrum, instead of peaking in the optical, shifts to the infrared. So the hallmark signature really is red emission to detect our process nucleosynthesis and the radioactive decay of very heavy elements. So here's an infrared spectrum where you see these two broad bumps because velocities are so high. There's so many line transitions that all blend together. And in red, what you see is a model prediction by Professor Dan Kaysen from 2013, 4 years before the gravitational wave event happened. And this is not trying to fit the data. This is just overplotting from an existing model suite. And there's a surprisingly good fit to what you would expect from our process nucleosynthesis and what we saw on that day. Now, spectroscopy is an extremely powerful technique. This is what gets you to the heart of the astrophysics. So please pay attention to Professor Robert Quimby's session 8 on Thursday on spectroscopy. Now here you see how the spectrum actually changed as a function of time. So on the top right corner, you see the time, and you see how there was this bright blue flash that let us detect GW170817 very easily, and how this emission gets redder and redder. And there's a lot of debate and a lot of detailed studies right now on what the different bumps and wiggles in the spectra and which elements did we actually see in the spectra and which elements did we not see in the spectra. So the question really in everybody's mind is that, okay, so these seem to be very prolific sites of our process nucleosynthesis. Heavy elements were definitely synthesized. So is our neutron star mergers a site or the site as far as the production rate of heavy elements goes? So what you see in this plot here is the solar hour process abundance. And this is the amount, how much of each element between atomic mass level 70 and 200 do we have in our local solar neighborhood. You see the distribution on the left and the cumulative distribution on the right. And you can see that most of what we see in the solar neighborhood is first peak. So that's the lightest of the heavy elements, not much of the heaviest of the heavy elements. And if you look at this neutron star merger, then most of what we saw, especially the light curve in the first 3 weeks, is easily explained by just the first peak. You don't necessarily need the second peak and third peak. But if you multiply it by a rough rate, you get roughly the right number. So it's in the ballpark of the observed solar abundance. But now a lot of people are interested in the third peak, especially the media, because element number 195 and 197 on that third peak is gold and platinum. So the question is, did we actually strike gold? And the good news is that even though we couldn't really answer that based on the first few weeks of data, on day, a month and 2 months later, the Spitzer Space Telescope was able to continue to collect mid-infrared data at 4.5 microns. And at late time, months after the merger, the beta decay heating rate is dominated not by elements in the first peak, but by elements in the second and third peak. That's just the radioactive half-lives of these elements. And so if you wait long enough, then you can figure out the answer to this question of whether the heaviest of the heavy elements were synthesized. And if you are able to tackle this data set from the Spitzer Space Telescope, you have this really bright galaxy and then this faint little red dot that is shown by the arrows there that you're trying to detect, then you need to master the technique of image subtraction. And this technique of image subtraction is what postdocs, growth postdocs, Christopher Fremling and Igor Andreoni will go over in some detail with you on session 6 on Wednesday. And you'll understand then how to subtract this bright galaxy light to detect this faint emission that tells you that we did strike gold. And then you would ask, what is the rate, right? I mean, I just put a squiggly at 500 per gigaparsec cube per year. And your head TA for the school, Igor Andreoni, just published a lovely paper on this topic. So please bug him about this. And he can tell you what all the different rate estimates for neutron star mergers is and how he did his own rate estimate. And you can go into a detailed discussion with him about this topic. Now, the question is, okay, GW170817 is fantastic, but if it is to explain all of the heavy elements that we see around us and we take for granted here on Earth, then the big question is it the norm or is it an exception, right? What does the distribution of heavy elements synthesized by neutron star mergers look like? And in the last year, even though we've tried following up every single trigger that had a neutron star in it, we didn't detect a kilonova. And we wrote a paper recently explaining our results in the past year. And you can speak to graduate student Shreya Anand, who will be one of your TAs as well. And she'll tell you why we believe that GW170817 just was not the norm. In fact, majority of events are likely fainter than GW170817 intrinsically. Okay, so that's enough detail about nucleosynthesis. Now that's all sort of centered in the middle of the spectrum, the UV, optical, infrared. Now let's go back to the other two extremes, the radio and the X-ray, and let's talk about the jet physics, right? Let's specifically talk about this question about are neutron star mergers indeed the progenitors of short-hard gamma ray bursts? And this was predicted that back in, again, 1989 by Boden-Paczynski and Eichler. But let's see if it, how much water this theory stands when you actually see a neutron star merger live and in action. Now, understanding and working with the radio and the X-ray data sets comes with its own challenges. X-ray because it has too few photons, and radio because it has too many photons. And so there are some special techniques you need to master there. And Dr. Brad Senko and David Kaplan will tell you more about these on sessions 9 and 10 on Friday. Now, what you learn from the radio and X-ray here, you can't learn from any other piece of the electromagnetic spectrum. So you may have noticed that I was using this word burst of gamma rays instead of gamma ray burst. So that should become more clear to you why I'm being so particular about the words after the next few slides. So what is a gamma ray burst? So say you have two neutron stars merge, you have a black hole, you have an accretion disk, you launch a jet. Now if you're looking down the barrel of the jet, straight down, if the Earth is in the line of sight, then you see an ultra-relativistic jet, which has the Lorentz factor of 100, very, very high speed material. And you see this thing called a gamma ray burst. Now, in the case of GW170817, what we saw was something that was a factor of 10,000 times weaker than any other short-hard gamma ray burst. It was next door to us, that's why we saw it, but it was very, very wimpy intrinsically. So what this suggests is that instead of looking down the barrel of the jet, we were looking slightly away from the barrel of the jet, right? Because the luminosity in the gamma rays drops by delta theta to the 4th power, with delta theta is in radians. So even if you were just 0.1 radian off, that could explain the drop in gamma ray luminosity. Okay, so everything's fine until then. The problem is that if you were at 40 megaparsec, which is what this NGC 4993 galaxy was, and you were only 0.1 radian off axis, then at the same time as you see the gamma rays, shortly after you should see the X-ray and radio afterglow. But as hard as my X-ray and radio colleagues tried, and they had very, very deep observations at early time, they didn't see anything in the radio and X-ray for about 9 days. So if I ignored the gamma rays, and I just look at the radio and X-ray data, that means that we couldn't be just slightly off axis, we had to be very off axis. So the Earth would have to be somewhere here to explain what the radio and X-ray saw. Now, so far, we live on only one planet Earth. Our satellites are not that far from us. So we only have one line of sight. So it's very inconsistent for two different pieces of the spectrum to suggest two different lines of sight. So this was very surprising. We knew this was not an on-axis GRB. We knew this was not a slightly off-axis classical GRB. And we had these two surprises that I explained to you. And we had a third surprise from this light curve plot, which was that it was much too bright and much too blue at early time than any theorists had predicted or expected. So what the growth team did to synthesize all of this was present this model that Professor Udi Nakar at Tel Aviv University came up with. And the model here is the Cocoon breakout model. So let me explain that. On the left, you see energetics, on the right, you see kinematics, okay? But what's actually going on is that when you have your neutron stars merging, you have tidal disruption, you have lots of stuff all around the merger event. So when the jet gets launched, it doesn't get launched into this pristine, clean environment. The jet gets launched into a very messy environment. And in this messy environment, the jet gets stuck. Instead of just cleanly shooting out, it starts to transfer energy into the surrounding material, all the tidally disrupted ejecta of the neutron star mergers. And so what you end up forming is not a narrow jet, but a very, very wide angle cocoon that is mildly relativistic. Now, by mildly relativistic, I mean Lorentz factors between few to 10. So it's still 0.99 C, but it's not 0.99999 C. Okay, so it's a relative term, but you form this very wide angle jet. And the advantage of it having a wide angle jet is that when this jet actually breaks out from the surface, because it's mildly relativistic, the gamma rays are weaker. And because it's slower, the X-ray and the radio emission is delayed. So very nicely, and because things have been Lorentz boosted, you get this bright blue emission. So very nicely, it could explain the different puzzles that we saw in the early data. And this model also had a prediction that if this model was right, then if we continue to observe GW170817, which we did, the radio and X-ray emission, even though we had to wait a whole 9 days to see it, it would last for hundreds of days. And that's exactly what happened. So let's take a look at that. Oh, and one more thing I should say is you could ask the question, okay, the cocoon broke out and powered the early emission, but what happened to the jet? Did the jet get completely clobbered by the cocoon and was it choked? Or did the jet also escape? And if we had a friend in an alien civilization at a different viewing angle, did someone somewhere see a short-hard gamma ray burst? And it turns out that when data was collected for hundreds of days after GW170817, we saw this lovely cocoon-powered rise, and then we saw this turnaround and the steep fall. And the steep fall was a clue that the jet did survive, and that there was a narrow and powerful jet, much too narrow and much too energetic for normal short-hard gamma ray bursts, but the jet did definitely survive. And that's what explains this steep decline here. So let me put all of this together into a nice NASA cartoon here, where you see the two neutron star mergers coming around each other, all this tidally disrupted material. You see the merger, black hole, accretion disk, jet, cocoon. You see all the radioactive decay from heavy elements that's making this bright blue flash into a very red event. And then you see the interaction with the circumstellar medium, which is lighting up the radio and the X-rays and telling you about the jet physics. So I'll leave you with that video in mind, and thank you for your attending the Virtual Growth Summer School. And I'll leave you with this last slide here, which has the link to the school and where you can find all the lectures and modules. Thank you very much.